displacement of the object. So what do we do? With an object having a rough surface, you have this phase, that is, if you have a rough surface, the moment you shine light, it gives you a random phase variation. It moves in the random manner across the object wavefront. So as a result, you will have the corresponding points on the object wavefront, and then you can reconstruct them. So this is what you can evaluate the phase difference. Consider one particular point like the previous slide. Consider one particular point B, and then you see how much is the shift. So that shift we calculate here, and that will be in terms of phi. So it becomes L into K1 minus K2, or that you can write as L into K. So displacement of P is small compared to the distance to the source S and the point of observation O. So this is a way how we can measure the surface displacement. One of the examples, one of the applications of this holographic interferometry. Then there is another important thing, which is what we call as the holo diagram. This you will find in the book by Hariharan or in many other books. So what is holo diagram? So holo diagram is a useful aid for the interpretation of the interference fringes. So for a basic hologram, like you have this hologram, you have the laser beam from here, use a reflector mirror here, that is creating as the reference beam, and here you have the object, and that you are measuring this. These are the psi angles K1 and K2. So you can measure this. So how it helps? Knowing about the fringe patterns. So for any object, point P, there will be an ellipse which it lies on the locus of the P, for which the distance OPO has a constant value. So you can create this kind of structure. Let me show you this kind of ellipses. So considering that those points. So what happens here? This is the equation which governs that. You can draw the circles through O and O prime as the curves of constant K. Then they correspond to the specified values of the parameter, and that parameter is Q, which is 1 by cos psi, and the psi is the angle which I showed you in this picture. Psi is this angle. So that is 1 over cos psi. And OPO prime is basically twice angle, twice psi. So these curves can be used to optimize a hologram recording system for the measurements of a particular type of surface displacement. So it helps in the surface displacement. So this is what we call as the holo diagram. So it has the benefit that it helps you. It is an aid that helps you to infer the details of this holograms. Then another application is strain analysis. This is again one of the metrological applications, the stress and the strain, you know. So inspection of the fringe pattern is quite useful to detect this localized defects and of the areas of stress concentration. So how to measure this stress? How to measure this strain? So how do we define? If you have at any point of the stressed object, then suppose it is Lx, Ly, Lz corresponding to the x, y, and z directions component. So you have this surface displacement, so that we can define as del x by del Lx by Lx, Ly component for Lz component. Then you can calculate the shear strains. So when you are taking the shear strains, then you have to take the x component and y component. So gamma xy. So del Lx by del y plus del y by del x. Similarly for the other component and the third component. So you will have xy, yz and zx. So we can calculate all these things. I think I have not worked in this area, but I think digital holography it would be very easy to calculate this, because these computations are easy now to perform. But this has been done earlier in terms of the optical holography. So what helps you once you have evaluated the surface displacement you have evaluated or you have measured, then you can calculate the strain. So this is how they are linked. So you calculate first surface displacement, and then you can display. Yes.
Displacement in plane or out of plane?
Displacement can be in plane or can be out of plane, both. So the moment this out of plane means you have this object. Now there are rotations also. This can move. It can move in this direction, or it can be in other direction as well. Rotation as well, like you have in plane rotation. So in plane rotation means like it is in the one plane, you have rotated this way. And out of plane rotation means you can rotate it this way, this way, this way. All possible. Like I am standing here, I can rotate. So it becomes out of plane. So it can be both.
So this analysis is extremely relative. So,
Yes.
so in case my reference sample already has, let's say, n strain in xy plane, if I start reducing the strain from n to n by 2, the next observation would be counted as an n by 2 strain.
Yes.
But actually I'm reducing the strain, so any way we can diagnose
It
that.
doesn't matter whether you are reducing or enhancing. So in a way, it is a interferometric technique. Like you have two interferograms. One still case, another one deformed case. So whether you are enhancing or compressing or decreasing, they are different states. So these are the applications of this interferometry. So you can have this strain calculation, and then it becomes very easy putting them into this matrix formulation, and MATLAB is the best tool for calculating that. So yesterday when I was looking at this, I thought that this would be very easy to do in digital holography. We have not done it for any such applications, but I have not seen the literature also, but people must have done it, because nowadays lots of applications of this digital holography for such applications. Like I was in Finland, I saw there was one sponsored project in Finland. The project was from paper industry, the paper industry which produces these papers. So what do? They will put these papers into water, tear into small pieces, so it becomes the strains of the fibers you will be able to see, and then they will place those samples into the digital holographic setup and check the fibers strength. Accordingly, they will decide which paper can be reused, which cannot be reused. So if the paper is not of good quality, you cannot reuse them, then they will send it for different purposes. Like making cartoons, making some other things, for packing materials, like that they decide. So in the industry, they have lots of samples, and they keep on imaging and taking the strength of the fibers, and accordingly they decide. So it was a very good project from the paper industry in Finland, because Finland produces lots of papers. They have lots of trees, so they cut and produce papers. It's one of the applications. Like that, there also you check these things. In one of the applications about what Kedar was talking about, the digital holographic microscopy. We were also working on one of the projects. Maybe I'll show you those images for the testing the drinking water quality. Like drinking water quality, how do you taste? Normally the tests are done periodically, 15 days or in a month. They will take those water and into the laboratory and check them. So what they had proposed, that we will put a digital holographic setup, a very combined small setup, at the point of the source from where the water is being distributed in the city. So there the water flow, we will place the camera, so the water flow will be monitored online all the time. The water is flowing, you have the camera, so if there is any extra element, any bacteria, smaller size or anything else, that will be imaged immediately. That this microscope is not going to tell you whether the water is drinkable or not, but it will keep on monitoring. Otherwise, if the waterborne diseases, there's something find that some disease has been spread here, then they will go and taste. So what is such device is going to help you? It is going to help you every hour, every minute you can monitor whether this water has some impurity or not. Some extra element is available in the drinking water. So these are some of the applications, direct applications. And again, some of the applications in, I think in US itself, I have seen some papers that they place this camera, even they have made it with the mobile phone cameras, that the patient is in remote place and they have to undergo some test and they have some reports or something to be imaged, that will be imaged with the mobile phone camera, and that it is not a normal image. Normal camera you will get this two-dimensional in photography, but with that concept you can create a 3D picture. It is not exactly 3D but more than 2D. So the doctor will have the real-time access and then they can prescribe medicines. So such medical aids have also been developed. So this is about this strain calculation. I have taken one problem here, one tutorial problem. So read this question. I am going to give you the solution because I found this problem interesting. So a hologram is recorded of a flat circular diaphragm clamped by its edge over an opening in a pressure vessel and illuminated at 45-degree angle with a beam from a helium neon laser 633 nanometer. The hologram is processed in situ and the diaphragm is viewed along the normal to its surface through the hologram. When the pressure in the vessel is increased slightly, 3 dark circular fringes are seen surrounding a dark spot at the center of the reconstructed image of the diaphragm. What is the deflection of the center of the diaphragm? Is the question understood? Little bit?
How much pressure we applied this?
Yeah, you just have to find the displacement.
Yes, you have to find the deflection.
Yeah, that's it.
I am going to give you the solution also. So since the edge of the diaphragm is fixed, we have 4 fringes from the edge to the center. So what will be the phase difference? So we have to calculate the del phi. So del phi, as you know, it is 4 fringes. So the formula which I yesterday also I talked about, it was 2m pi. So here m is 4, so we are talking about the 4 fringes. So it is 4 into 2 pi. And we also know that the displacement of the center of the diaphragm must be along the normal to its surface. So what would be the magnitude of the sensitivity vector, that is the capital K. So capital K, it is going to be 2 pi by lambda into 1 plus cos 45 degree. Phi is your 45 degree. So calculate cos 45 degree, so it becomes 1 plus 0.7071. Lambda is mentioned, helium neon laser 633 nanometer, so 633 into 10 raised to the power minus 9. So calculate this one, it becomes 16.94 into 10 raised to power 6 per meter. This is your sensitivity vector capital K. So displacement of the center of the diaphragm, this is what the question is. So it is nothing but the del phi by K. So it becomes, substitute it here, it becomes 1.48 micron. I'll send you this slide, so don't worry. Just for the sake of practice. Okay. Yesterday somebody asked about this Moore pattern also. So what is Moore interferometry? So as I said yesterday that you take one net or anything you can, in many ways you can produce Moore patterns. So image of a master object and a similar test object are superimposed. It is just superimposition. Superimposed by means of a suitable optical system. A hologram is recorded of the resultant wave field. So this is the intensity of that hologram will be represented this way because you are taking superimposing. So here you have two terms, cos phi 1 minus phi 2 by 2 and plus phi 1 plus phi 2 by 2. This is the term which is going to be very useful for the measurement purposes. K is the sensitivity vector. So an observer sees Moore fringes generated by the term this phi 1 minus phi 2 by 2 with which contour the differences in the displacement of the two objects. This is how you can produce Moore pattern, Moore interferometry. So since somebody asked, so I thought I will include that. Again, the last part is the vibrating surfaces.
So
I showed you the guitar.
I wanted to say maybe then, we did a lot of work, some work I should say, on Moore and finding the displacements and the map. So maybe tomorrow I will show an example of how you can use the Moore patterns. And also that shift, as he was talking about, the shift of the phase, we also found that using phase shifting principles.
Yes.
Because you can, that's a way to find out unknown phase. So it will be a good combination, I hope, of this Moore and phase shifting.
This is very good research area. Moore is very good. And the best part is you don't need a laser light.
It's just
You don't need. So if you don't use a laser light, the speckles problems have gone. So that's a benefit. So this vibrating surfaces. I showed you the image of the guitar. So here the same thing I have just wanted to add. So for solving such type of problem for this vibratory systems, so we have one technique called stroboscopic interferometry. So what you do in this case? So you have a hologram of the vibrating object, which is recorded using a sequence of light pulses. You have to use a pulse light, of course, that triggered at two different times. One is delta T1 and delta T2, because you have to have at different timings, then only you can compute the vibrations. So after the start of each vibration cycle, so that if the displacement at some point is xy on the object at time t, so this is how we can give displacement Lxy to sine omega t. So what would be the intensity? Again, you have to combine for these two different timings, so sine omega t1 and sine omega t2 for two different timings. Once you have this intensity, so as usual, K is the sensitivity vector, and you have this term I naught xy. So I naught xy is the intensity in the image when the object is at rest. So it is not the vibration. When it is at rest, that time the intensity is I naught xy. So this hologram is simply the equivalent to a double exposure. Means you are taking recording one hologram at delta T1, another at delta T2. It is similar to the treatment is similar to the double exposure interferometry. And you come to know the another one is that time average interferometry. This I showed you that picture again. So here important point is that you have to have the exposure time should be long compared to the period of vibration. If it is not longer than the period of vibration, then you won't be able to record any information. So this is very important here. So it has lots of mathematics. So suppose one of the phases I am taking at k into L, then sin omega t. Then you have the complex amplitude of the scattered light wave from the vibrating object. So if the holographic recording process is linear, then you have this complex amplitude of the wave reconstructed by the hologram. So you have this expression for the optical field when you are averaging over the time. So this factor mtxy is the characteristic function, and you can represent it for the time 0 to 2, you have to integrate it. Then this gives rise to the function value of J naught. This is what we call as the zero order Bessel function. The intensity you can represent this way. We can plot them, and if you are plotting them, one with the characteristic function for the A is the time average fringes and B is the real time fringes. So you can plot them. So what do you observe here? That the vibration amplitude varies over on an object. It gives rise to fringes, which is the contours of equal vibration amplitude. That covers the reconstructed image. You will have the dark fringes at will. Dark fringes, the intensity drops to 0. Correspond to the zeros of the function that will be corrected by this expression. This is the Bessel function. And bright fringes to its maxima. You have the first maximum that corresponds to the nodes, and this is what you were asking me, nodes and antinodes. So this is what corresponds. So the first maximum will correspond to the nodes, that's the brightest, and while the intensities of the successive maxima are occurring at larger vibration amplitudes fall off progressively. So if you see that at different timings, such images, this is how you can see time average holographic interferograms for different frequencies. So A frequency is 195, B is at 292, C is 385, D is 537, like that. This is what is the time average interferometer. I think that is all about this, and I'll take few minutes to just to tell you about the phase shifting part, because no, not sorry, not phase shifting, phase contrast part. So maybe if time permits, there is one of the good applications of this holography in the holographic solar concentrator that helps in enhancing the solar concentration. Just quickly take 5 to 10 more minutes, sir, just to explain this phase contrast. Okay, before coming to the phase contrast, because this is what I teach to my students in the okay, sorry, this is not. Okay, so scattering is very important phenomena associated to the holography. So this scattering is of three types. You all know about the Rayleigh scattering, for which the sky is our blue. So then we have two more types, one we call as the Mie scattering and non-selective scattering. So Rayleigh scattering mainly consists of the scattering from atmospheric particles or atmospheric gases, where the basic condition is that the particles which causes scattering has to be smaller than the size of the wavelengths of the light, and it is just reverse for the case of the Mie scattering. So this is one of the examples of the Rayleigh scattering, and Mie scattering is caused due to this pollen, dust, smoke, water droplets, which is larger than that size of the atmospheric particles. And then we have this non-selective scattering, which causes in the lower portion of the atmosphere, where the particles are much larger than the incident radius. So these are the three types of the scattering. Okay. So coming back to the phase contrast. So what will happen when you have the material and you allow the light beam to pass through it? In some cases we say some object is, if I shine a light will not go out of this room because this wall is a opaque object, it doesn't allow the light beam to pass through. But if I use a X-ray, that will pass through. So what will happen when the light interacts with the material? So three things are going to happen. The object can be transparent, non-absorbent material with higher refractive index, right? Second can be transparent and non-absorbent but thicker. It is not absorbing but it is thicker. Third is, it is transparent and absorbent. So if the object is absorbent, if you see that color is blue because the blue wavelength is reflected. And if you have an object which doesn't absorb anything, so blue means blue color is reflected, all other wavelengths are absorbed by the object. So suppose here the light beam is simply passing through the object. It is not getting absorbed by the material. But what will we say? It is non-absorbing material. Like you see a very clean glass window, which is very clean. Sometimes it gives you an effect that you suddenly want to get into the room and you hit the door. Because it is transparent, fully transparent, and you are not able to visualize that there is a door. But still technically, if you shine a light beam, those glass plates also reflect light. And there is a relationship between the reflectance and the transmittance. It depends upon the refractive index of that glass. Suppose the refractive index of the glass is 1.5, then the formula is R1 minus R2 by R1 plus R2 mod square. So it is 1.5 minus 1 by 1.5 plus 1. So ultimately 4% of the light is reflected, 96% light is transmitted. But still what we perceive is we perceive that it is transparent. So when we have this interference, so what happens? In case of interference, light rays undergo a phase change depending upon the refractive index of the transparent material. Phase change, it means, is in direct proportion to the thickness of the material. Whatever is the phase change, that will depend upon the thickness, because there is a relationship between the phase difference and path difference. So phase difference is defined as 2 pi by lambda into path difference. So light rays, third case is light rays undergo change in amplitude when it passes through an absorbent material. Amplitude will go down. So in case of phase objects, so more refractive index and thickness, more change in phase. So if a biological material absorbs light ray, that they show contrast, but living cells generally do not absorb light ray. Cells and their components don't show phase change. Value of phase change is 1/4 of the wavelength of light, but this phase change is not distinguished by our eyes. We are not able to see. So what is the tool? How we can see them? So what is the physics behind that? So principle behind this phase contrast microscope, we call it as the microscope, is to convert undistinguishable phase change, what we cannot notice through our eyes, into distinguishable phase change in terms of variation of contrast. With the help of two adapters, one we call as the annular diaphragm, another one is the annular phase plate. You will see one very important thing about the interference, and in the holography it is very important that you have the fringe pattern, bright dark fringe pattern. Contrast has to be very good. Contrast is also meaning the same thing as visibility. In this winter vacation time, if the flights are not landing, and they say visibility is very poor. So what technically we mean by the term visibility? Low contrast. So what do you mean by the low contrast? It is the ratio of the maximum and minimum intensity. If the dark is very dark and bright is very bright, then contrast is good. I give normally one example, that you watch television and you find many people sitting in front in the television studio talking to you, but they wear different colors of the shirts and cloths. Because if they all wear white, then you will not be able to see them. So contrast should be better. Understand? So contrast has to be better. What is its impact in terms of fringe pattern? Normally when we don't see fringes, it means contrast is very poor. Suddenly the contrast becoming poor, so the fringe pattern means bright, there you will not be able to distinguish where it is bright, where it is dark. So darkness starts losing darkness and brightness starts losing brightness, it becomes uniform. This is what we say destructive interference. When it is bright and dark, then we have constructive interference. So it is the contrast which decides. So this is very important in this case. So a phase object. What do we mean by a phase object? It means object is completely transparent but has an optical thickness which varies from point to point. So I gave you the example of a glass window. Its thickness can be at different point different, but it is transparent. It is one of the examples. I give another example, that you take a transparency.
In material I already prepared on the thick plane. That was fully transparent and thickness.
Yes.
But some mistake, there is no create any pattern.
Okay.
I don't know what is the problem.
And that can be discussed separately, I cannot say. But I am just explaining what do you mean by the phase object. So suppose you take a normal transparency on which we write and you use to project. You can buy from the market, it is available. So the thickness of the transparency is say 100 micron. Now you take the transparency and make a hole into it. Cut at some portion like letter O. Or you write something letter H. Then you create and cut the thing letter H or letter I. Now you keep in front of you, shine the laser light or even in the normal light. You have written letter I there because you have cut the shape of the letter I. But that letter I is non-absorbent. Light is simply passing through it. It is not absorbing any amount of light. But letter I is there. So some information is there. You are not, you have to measure, if you have to image, you won't be able to image. It will give you that impression, but you will not be able to image. That is a non-absorbing object. Non-absorbing image. Letter I what I have written. If you write letter I, that becomes absorbent. With the ink, if you write letter I, that will be absorbent. Here it is non-absorbing. So how to measure them? So it introduces phase difference. How it is introducing phase difference? Because the thickness of the transparency is 100 micron. So where you have cut it or you have removed the transparency or where it is there is a path difference between these two. So that will correspond to the phase difference, 2 pi by lambda into phase difference. So it is a phase object, it has some phase. How much is the phase? You can calculate. So it introduces phase difference between disturbances which pass through different parts of it. So consequently disturbances immediately behind the object and in conjugate image plane have some same amplitude at all points, but will show variations in phase from point to point. So human eye is sensitive to intensity only and cannot detect changes of phase, so that field of view appears uniformly bright. This is what is the phase. Now the question is how to image them, and this was the problem which Jernicke solved, and he got the Nobel Prize in 1935. So this is what the solution is. You have the incident light, you have the strained cell, here you have the waves in phase, and you have the unstrained cell. So what he suggested, will be explained here. Let me go through this slide first, then I will get back. Very easy thing to understand from here. Suppose I have the phase object here, exponential, mathematically this is how we represent. Use a lens to take its Fourier transform. We are in the Fourier plane. In the Fourier plane, you will have zero order diffraction, first order, second order diffraction. So in the zero order, what Jernicke suggested, we will introduce pi by 2 phase shift. All other orders of diffraction remain same. Only zero order, and zero order you can calculate. It depends upon the aperture and the wavelength of the light. So what would be the dimension of the zero order that you can calculate? And we can create a filter. That filter, like transparency, it is able to introduce pi by 2 phase shift only to the central order of diffraction, and all other diffraction orders it is uniform. Alright? Now what will happen? Take one more Fourier transform. So the wavefronts, the central order wavefront is pi by 2 phase advanced, all other orders remains in the same wavefront. They will interfere, and then they convert phase image into an intensity image. And this is what is called as the phase contrast. And this is what was done by Jernicke. So he called the filter which is introducing pi by 2 phase as the annular filter. It is called as the phase contrast filter. Kedar was also mentioning the same filter. This is the phase contrast filter. So this is what is shown here in this case. This is the phase plate. It's called as the phase plate or phase contrast filter. In different books, different names are there. Now quickly I'll tell you what, this is one of the examples. This E. coli, it is a phase object, but it has been imaged through the phase contrast microscopy, and you can see the E. coli. So it means the phase function has been converted into amplitude. In few minutes, what is physics? How we are converting? I have understood the concept, how you can do that. What is physics? This is the way we can represent a phase object. Now, any exponential function, e to the power x, can be expanded in this way. This is how it has been expanded, e to the power I phi xy. So 1 plus this, second term, third term, like that. So Jernicke suggested you take it up to the first order only. So for mathematical simplicity, assuming the object has a magnitude of unity, so you have the finite extent of the entrance since the aperture, and exit pupils are neglected. Because those factors what sir was talking about the Fourier optics, we have omitted here. But you have to consider everything if you are actually working for any problem. So also there is a necessary condition to achieve linearity between phase shift and intensity. So condition is that the variable part of the introduced phase shift, which is delta phi xy, should be small compared with the 2 pi radians. So once you apply that, so this is what you are going to get. If you apply this phase shift, so you have e to the power I phi naught into e to the power I del phi. So expand it, it becomes e to the power I del phi, del phi naught 1 plus I del phi. And if you take the intensity, it becomes 1 because exponential term will go away. This is the main problem. So how to address this problem? So addressing is, if I introduce this pi by 2 phase plate here, then this term will is as this plus this. So what you get out of here, it is become 1 plus twice phase del phi pi xy. I term is not there. It means you are able to measure the phase function here. So if you can introduce pi by 2 phase plate, or you can introduce 3 pi by 2 phase plate. Either way. If you introduce pi by 2 phase plate, we get the positive phase contrast. If you introduce 3 pi by 2, then what you get is the negative phase contrast. This is what is called as the phase contrast microscopy. Now this concept, which was given long back by Wernicke, it has been further modified. And it has been further modified by a group of scientists from Denmark. His name is Jesper Bukestad. So what he suggested, in this case, if you go back to this this expression, you are expanding this exponential term. So in case of Wernicke, he was considering only up to the first term. Higher order terms he has neglected. So this Jesper suggested that you should consider higher order terms also. If we consider higher order terms, it means those higher order terms do carry some information. We should not ignore them. So if you consider them and then you make a filter, so this pi by 2 phase requirement has gone. In that case, you need to introduce a filter of pi phase shift, and then that gives you much better result as compared to this one. So that has been named as generalized phase contrast. So that's another way you can do it.
So these are the higher diffracted orders?
Yeah, no, not higher diffraction orders. These are the higher orders of expansion. You are expanding this e to the power I phi, e to the power I theta, you know. So you have e to the power I theta different terms. So in case of Wernicke, only up to this was considered.
Yes.
So Jesper suggested no, you can consider higher order terms also. It means the mathematics becomes lengthy, you have to solve it longer. But finally, what is the result? Result is you introduce a pi phase shift instead of pi by 2 phase shift, and that gives you much better. So I think I'll stop here, sir.
That's good, very nice.
So this is what I wanted to tell you, because Kedar had talked in between, so I thought if I don't say, you may not be able to connect what he was saying. Any question?
So there is a negative phase contrast also?
Yes.
Like the positive.
Like if you write IIT, so it will be one case bright IIT, other case dark IIT. So this is what we call, this is what practically mean.
Because I think that have another advantage because our eye is sensitive in the lower.
Both the cases. Sir, you can
So
say.
are there any other advantages of making a pi phase shift?
Yeah, it has many advantages. I have used it for security purposes, or it gives better result as compared to the pi by 2 phase. And then there is one restriction which I mentioned here. That restriction is what type of phase image you can calculate. Here is the condition. Condition is value of the phase change is 1/4 of the wavelength. Means lambda by 4 change is there. That only you can measure with the journey gauge phase contrast. But if the phase change is larger, then that doesn't give you good quality result.
Yes, exactly.
And this is where this generalized phase contrast gives you better result. So it means if the phase value is less, then you can measure with the phase, this pi/2 phase shift. If the phase value is more, then you have to go to the pi phase.
So means experimentally we just need to
Replace the filter, all other things remain same.
numerically.
Yes, yes. I have done it even without, this was one of my PhD problems. So that time we didn't have this facility, so I had to run to many people because I have to have a filter. For preparing a filter, we had to have a glass plate and put that IPO coating onto that. Then somebody had to do the etching perfectly with that size, matching, calculating the zero order pattern depending upon the wavelength and the aperture dimension. So once I did it, that failed. I did not get any result. So then I thought that okay, I have to introduce pi phase shift only. So the SLM has the benefit. I can introduce pi phase shift. So what we did, we created a transparency of the size of the dimension of the SLM and created a black spot dot exactly matching to the zero order. So what happened? Whole transparency was blank, white, and central portion was dark. So that introduced some phase shift, and it resulted into good result.
Actually, coincidentally, last semester we have, like, the students, they have just assembled everything to make a phase contrast microscope.
Okay.
Not like this commercial one, but on the optical bench.
Yeah, you can do that. You can do that.
But
But what was critical that we had to work hard because the central order should exactly match the position where we are introducing pi phase or pi/2 phase. So this took some time initially in getting it familiarized and getting that expertise. Then you can do that.
actually we
I have done it for
used,
security applications. So, but you can do it for many other applications.
I mean, we used laser just
Yes.
instead of white light. But the problem we are facing is because of the laser only we are getting additional diffraction pattern.
Yes, that gives.
So
That.
that is,
Even that happens with the case of SLMs also, because SLM is a pixelated device. It gives you the diffraction orders.
so that you can discard only numerically, I mean, or is there any other way?
No, there is no way because it is inherent. It is inherent. It will be there. So you have to have some technology developed indigenous because there is no ready-made solution to it. You can do that.
So probably that is why people use this white light
Yes.
to discuss.
So
Okay.
can we see only through the simple microscope? Yes.
This is a microscope. You don't have to use any other microscope in this one. This is a microscope. What microscope is doing? You have a simple microscope, the best thing. Start with a simple microscope. I ask one question to my BTech students. How much is simple microscope? What is the example of a simple microscope? Magnifying glass. This normally magnifying glass, how much magnification it can give?
10x.
No. It depends upon this 25 centimeter distance.
Oh, yes.
So, maximum it can give is 20 to 25x. So, any one lens will give you 20 to 25x amplification. So, you have to have if you want more magnification, then what do? One lens is not enough, so we use two lenses. That is why we call it as the compound microscope. You have one this objective, another one is the eye. So it means it is doubled. But doubled means again, you use a microscope objective that will be of multiple elements. So there you have the more flexibility to play with that. Okay, so let me unshare.
But sir, if we use white light in your examples, won't we have to consider chromatic aberration?
Aberration will be there.
But laser would have coherency and then speckle patterns and lot of those things. So what should we choose? What should we prefer?
See, white light is also coherent light.
Yes, but we won't be facing speckles as much as we do.
Technically, white light is also coherent light. It has very small coherence length as compared to the lasers. So basically, in the beginning, people, when the lasers were not there, people were using white light only. And the white light gives you very good quality fringes because that will be colored fringes.
Oh yes.
But it was very tough for anyone to do that, such experiments.
Order of few millimeters, the coherence length.
No, not few millimeters. It is in micron.
Oh, okay.
Well, I have to image water waves, as I was talking. My
Yes.
PhD was on water waves. I had to image water waves. And on a, you know, those big things used to be there before, this overhead projector. Overhead projector gives out white light.
Yes.
And then all I did actually, as you know, Dr. Nishchal said, is water waves were flowing on a tank on top of there. And then I just put a small, that black spot or a small dot. And that was good enough for me to see the phase contrast. And because I had to see the surface of the water, how it's vibrating. But that was good enough to do it.
So in research, you have to develop your own indigenous ways to solve the problem. Because if the solutions are available, then there is no point of research.
That's right. Very good, thank you very much. So that's it. How are we doing on time?
So it is 12:30.
So we can. So maybe I'll talk a little bit, continue along yesterday, a little bit of the phase unwrapping. I'll talk about that, you know, doing the digital holographic reconstruction. And then go and talk about also, continue along the lines of what Dr. Nishchal was talking about, which is holographic interferometry. That's another application. I'm going to illustrate an application, but go over it in some detail. See how you can measure distortions. So that will be hopefully a good one. And then later on, I'll start talking about the phase shifting. So let's see, I need to again connect this. Oh, someone has to set this up with that
ये
wire.
उसको बुलाना ना
Unless there is a cord.
नीरज बाहर होगा.
Right, we have to do
But
that wire.
connect automatically. Ah, yes.
But then, how do I get to that C-scope? Let me see, maybe I have C-scope.
No, but you have to use the same link. Yeah, he'll come.
Yeah, actually, I don't know that link.
Yeah, he will use that.
Okay, let's start here.
So any question from the online participants?
Oh, thank you again.
transparent. Like you have seen the diffusers, बल्ब लगाते हैं ना घर में, तो बल्ब की तो रोशनी एक ही जगह आती है, उसके ऊपर एक प्लेट लगा देते हैं, उस प्लेट लगाने से बल्ब नहीं दिखता लेकिन रोशनी पूरे फैल जाती है, इससे डिफ्यूजर, so that's the same thing. इसलिए डिफ्यूजर नहीं, बेनिफिट नहीं है, बेनिफिट है भी कहेंगे, बेनिफिट नहीं भी है, वो तो एप्लीकेशन पे डिपेंड Today we will have his talk also in the afternoon. We'll talk on the terahertz technology. Yes. हाँ, क्लिप तो मिलेगा ही ना। कोई भी फंक्शन है, ग्रेटिंग कभी देखा है आपने? ग्रेटिंग यूज किया है? टॉर्च डालिए ग्रेटिंग में तो क्या मिलता है? ऑर्डर मिलता है ना? 0 ऑर्डर मिलता है, +1, +2, -1, -2। तो डिजिटल होलोग्राम जो है, जो आपका होलोग्राम है, it is a interference pattern. It is nothing but like a grating. And taking one more Fourier transform means you are taking the diffraction of that hologram. So this will also have, it will not have only 2 orders. It will have many orders, both ends. Like you take the integral, parallel integral, -infinity to +infinity. -infinity to +infinity. So diffraction orders are infinity. But हम कंप्यूटर में देख नहीं सकते. So you will be able to see only 2. And what happens? You have the second order, third order. Because your computer is not capable of showing all the orders. So जो order है extra वो कहाँ जाते हैं? Where they will go? They will start wrapping. Yes. And this is what sir is going to talk about, how to unwrap them. Because those are not desired.
That's a good rap music.
Exactly.
Is the point clear? ठीक है ना? जो ग्रेटिंग भी ऐसे ही बनाते हैं। Nowadays जो ग्रेटिंग बनाते हैं, एक्सपेरिमेंट में यूज करते हैं। ये क्या होता है ना कि in one inch you have 10,000 lines. So drawing 10,000 lines, if somebody says you have to draw 50,000 lines in 1 inch, who will do that? It will be extremely difficult task. But as a holographer, you can do it in 1 minute. You have to shift, you have to change the fringe spacing. So fringe spacing will depend upon your angle when you are recording the interference pattern. So there you can control the fringe spacing, and if you want 10,000 lines or you want 20,000 lines or 50,000 lines, everything you can do that.